All right, well, thank you all for coming, and thank you to the organizers for the chance to speak here. So I'll be speaking about some recent work that I've done with Kannan Soundararajan of Stanford on sort of the distribution of consecutive primes, particularly consecutive primes in arithmetic progressions. And so I'm going to talk some about some work we did close to a year ago, and then also some kind of toward the end of the talk about some recent developments and some connections of that work to some sort of surprising sort of other areas in analytic number theory. But to begin and sort of really put our result in context, to sort of really properly frame it, I'd like to start off sort of by talking about Chebyshev's bias. So let pi xqa denote the number of primes up to x that are congruent to a mod q. And it's well known that under GRH, the primes are very well distributed sort of among the admissible residue classes modulo q. So in particular, sort of each residue class sort of has its fair share, and then there's a square root error term, where of course here, this is where I am using GRH. And so what this formula says is that sort of all of these sort of different residue classes are equally likely as far as this formula is concerned. But nevertheless, Chebyshev observed that certain residue classes seem to be favored over others. And in particular, there is a preference for quadratic non-residues over quadratic residues modulo q. But this phenomenon sort of necessarily has to live sort of at the level of this error term. Kind of has to live at sort of the level of the noise in this equidistribution result because there's no other place for it to live. So that's something about zeros of L functions. And exploiting that, Rubinstein and Sarnak, in Rubinstein's undergrad thesis, proved that under GRH plus a bit more, or maybe quite a bit more, that, for example, you can make statements like pi x32 is greater than pi x31 99.9% of the time, where this is sort of a legitimate 99.9%. There's a 0.1% chance that there might be more primes that are 1 mod 3 than 2 mod 3. But sort of for typical values of x you pick, you'll see more that are 2 mod 3 than 1 mod 3. And analogous statements hold for any modulus q. So being analytic number theorists, and in particular sort of looking at the primes, we're in a very privileged situation where we're sort of talking about very explicit objects. Chebyshev's bias is a very explicit phenomenon, and I'd sort of be remiss if I didn't actually show you what it looks like. So if we look at the first 1,000 primes, modulo 3, kind of already we can see basically everything I've had on the previous slide. You see very clean equidistribution between the two admissible residue classes. And you see this preference for primes that are 2 mod 3 over 1 mod 3 corresponding to the fact that 2 is a non-residue and 1 is a quadratic residue. And if we extend this data farther and farther out, the picture becomes sort of clearer and clearer. We can see sort of this consistent preference for primes that are 2 mod 3 over primes that are 1 mod 3. But it lives sort of in this kind of noise in the equidistribution. It lives in the noise. That's sort of what I want you to observe here. We could look at this for some other modulus. For example, mod 4, the data looks basically the same. Things are slightly more interesting. If we look mod 5, more residue classes to work with, more sort of room for sort of interesting behavior. And particularly if we look at the first 1,000 primes, again, already we see very clean equidistribution. Sort of each of these counts is very close to 25%. And we see a preference for the classes 2 and 3 mod 5, which are the non-residues, and 1 and 4 are the residues. And we see that these are slightly depleted relative to the flat 250 you might expect. But the reason why I put this slide up is not really to belabor this point so much as if we sort of continue extending this data, we actually see something that I like a lot. We see this sort of 0.1% type probability that an underrepresented class sneaks ahead. We see that there, sort of at this point, there are more primes that are 4 mod 5 than 3 mod 5, even though generally speaking, primes that are 3 mod 5 are preferred. And then sort of by the time we sort of look farther out, well, kind of order is restored. All right. Didn't plan that as a joke in my talk, but I'll go with it. All right. So this is a very beautiful subject. Kind of gave birth to some study of prime number races. There's been a lot of fantastic work done on this, even sort of very recently, within the last few years. But what I want to talk about today is something different than this. In particular, what Sound and I were interested in is what if we look at patterns of consecutive primes modulo q. So let r be greater than or equal to 1, and consider some r tuple of integers. And what I want to do is I want to count sort of primes for which the first prime is congruent to a1 mod q, second prime is congruent to a2 mod q, third prime is congruent to a3 mod q, et cetera. Okay? So I'm going to let this function pi xq bold a do exactly that. Okay? So it's going to count the number of primes up to x, for which sort of the first prime is a1, second prime is a2, et cetera. Okay? So what should we expect to be true about this function? Okay? Well, I think sort of there's no reason to expect that one of these patterns should be preferred over any other. Okay? I think it's very natural to expect that each of these patterns should occur with probability 1 over phi of q to the r. Okay? But actually, very little is known along these lines. Okay? So in particular, the only cases where we really know anything, the only cases where we even know the infinitude of the underlying set of primes, relies on there being some very simplified combinatorics. Okay? So the first case in which we sort of have these simplified combinatorics was observed by Napovsky and Turan. And they sort of showed that if you have two consecutive primes, and you're looking at a modulus for which phi of q is 2, okay, which is pretty limited, okay, so you're basically looking at consecutive coin flips, and that's it, okay, then you can show that each pattern occurs infinitely often. Okay? And this is actually a pretty easy argument. Okay? So to convince you of the fact that the primes have to switch infinitely often mod 3, well, just observe that there are infinitely many primes that are 1 mod 3, and infinitely many primes that are 2 mod 3. And so if you didn't switch infinitely often, you'd get stuck. To show that you sort of have sort of diagonal patterns, it needs a little bit more work, but it's actually pretty standard now, sort of in terms of modern techniques. Okay. The other scenario in which we know something about these sets of primes goes back to work of Dan Shu in the late 90s, okay, who proved that if you look at a very special kind of pattern, but for any modulus and of any length, then you can prove infinitude. Okay. So in particular, if you look at a diagonal pattern, so you can find 100 primes in a row that are 1 mod 17. Okay? Okay? You can prove that these patterns occur infinitely often. Okay? Shu's proof actually gives a quantitative lower bound. It's the form x to the 1 minus epsilon. Okay? But that result has now been superseded by works of James Maynard, who proved that these primes actually occupy a positive proportion of all primes. Okay? So you have a positive probability of finding 100 primes in a row that are 1 mod 17. Okay? But that's it. That's all that we know. As soon as you change one of these things to something sort of different, okay, we do not know that the underlying set of primes is infinite. That's kind of an embarrassing situation to be in, but such is life. Okay? And it doesn't really prevent us from asking interesting questions about these sets of primes. Okay? And in particular, what Sand and I were wondering is, are there biases between these different patterns, sort of analogous to what we saw with Chebyshev's bias? Okay? Well, what is there to do but to compute and take a look? Okay? Well, so here, again, we're sort of looking at the different patterns mod 3 of 2 consecutive primes. Okay? And by this work of Napovsky and Turan, we know that each of these 4 patterns occurs infinitely often. Okay? Let's go ahead and take a look at the first 1,000 primes. If things are completely fair, we should expect each of these numbers to be pretty close to 250. Okay? And this is what we see. Okay? That's not really very close to being equidistributed. And maybe you sort of worry that 1,000 primes just isn't enough to work with. And if we extend this out farther and farther, farther, it's clear that things are getting better. Okay? Sort of, it's pretty clear that sort of the limit of each column probably is 25%. Okay? But there are some real terms here that sort of are much, much bigger than anything we saw with Chebyshev's bias. We're sort of not seeing things that live at the level of noise. We're seeing legitimate terms here, right, that seem to be destroying our equidistribution. Okay? And so apart from that, what I want you to take away from this slide is I want you to notice which patterns are sort of relatively more likely and relatively unlikely. And in particular, I want you to observe that these switching patterns are more likely than the diagonal patterns. Okay. All right. We can do something similar and look at the data mod 4. Okay. It looks basically the same. Okay. Looking at primes mod 3 and primes mod 4, data looks almost identical. Okay. So things get more interesting if we look, say, mod 5. Okay. So there's sort of a lot more room to play around. There's a lot more room for things to go wrong. Okay. And if we look at the first 10 million primes, again, we sort of have the Chebyshev's bias type equidistribution. Okay. Each of these classes is very close to 25%, and there's a slight preference for 2 and 3. Okay. But what we're asking, what Sand and I are asking, is how do these 2.5 million split up if you stratify based on what the next prime does? Okay. So in other words, we're sort of asking, are each of these things going to be about 625,000, or are you going to see some variations like we saw on the previous slide? Okay. And in particular, if you look at this, what we find is this. Okay. And if you look at sort of all patterns, things get worse. Okay. So kind of the most obvious thing I want you to take away from this is that these numbers are all pretty different. Okay. You can find a couple that are suspiciously close to each other. We understand when that happens. Okay. But for the most part, you get sort of legitimately different numbers. And the second thing I want you to observe, okay, is that the patterns that are least frequent are, well, these diagonal patterns, 1, 1, 2, 2, 3, 3, 4, 4. Okay. Perversely, on this slide, those are the only patterns we know occur infinitely often. Okay. All right. And just in case you are not convinced that 10 million primes is enough, okay, you can extend this computation by a factor of 10. Okay, and it looks basically the same. And indeed, sort of one thing I'm fond of doing with these slides is switching back and forth here. And you can see that there's some sort of consistency in the terms. Okay? Things are getting better. They're getting closer to this 6.25%. Okay? But it's kind of, there's some sort of consistent behavior sort of forcing you away from it. Okay? So the question is, what is going on? Okay? And I'll make a technical conjecture on the next slide. But basically the idea, okay, is that Sound and I conjecture, okay, that, well, there are large secondary terms in the asymptotic for this function, for this pi x cubed bold A. Okay. That the dominant factor, okay, in these secondary terms, sort of the dominant thing creating a bias, is just sort of counting the number of repetitions in your pattern. Okay. So we've only been looking at patterns of 2 consecutive primes. Okay. So we're just asking, does A equals B or not? Okay. And that's kind of the dominant thing. But then there also has to be something to kind of create a lot of the erratic behavior we saw in the previous slide, sort of all of the different numbers we saw when we looked at these patterns mod 5. Okay? And we do indeed expect that there are some somewhat smaller erratic factors that control these. Okay? So more precisely, our conjecture looks like the following. Okay? So again, pick your favorite pattern of primes mod q. And what we predict is that the asymptotic formula looks like this. Okay? So we think that pi xqa should be equal to li of x over phi of q to the r. If life were completely fair, this would be the only term on the right-hand side. Okay? And so what I'm doing when I sort of have this 1 plus is I'm saying, how much are we deviating from this? Okay? And what we think is that you should have sort of a relative bias in the order sort of log log over log and 1 over log, which does indeed tend to 0, but it tends to 0 pretty slowly. Okay? And that's kind of what we see in this data. Okay? All right. So there are definitely lots of things I want to say on this slide. Okay? The first is, well, OK, I have this log to the -7/4 error. I think I imagine almost everyone has a question about that. Yes, we think that's the right answer. Okay. I might say some words about why we think that's the right answer. Okay. But yeah, it's sort of surprising. This means there's some log to the 7/4 floating around in nature, okay. Which I do find a little bit sort of quirky. But OK, so what are these sort of numbers C1 and C2? Okay. Well, C1 is actually very easy to explain. Okay. C1 is exactly what is sort of corresponding to this sort of bias against repetitions. Okay. So in particular, it's given by this formula, which maybe looks like a mouthful, but it's actually pretty easy to parse once you break it down. So this term here is just counting the number of immediate repetitions in your pattern, okay, that you wrote down. So again, if you're looking at a pattern of length 2, you're just asking, does A equal B? Okay. This term here is the expected number of repetitions in a random pattern. Okay. If you just chose A sort of completely randomly, how many immediate repetitions would you expect? It'd be this many. So you're just seeing sort of how you compare against sort of what a random thing would be. And then you're just sort of renormalizing this slightly. Okay. So it's this term that is going to create sort of this big bias against repetition. Okay. And that sort of means that this C2 somehow has to create all of this erratic behavior. Okay. And so that's sort of what we think happens. Okay. We have a complicated but explicit formula for what C2 is. Okay. And C2 is actually going to be sort of the main thrust, or sort of main focus of the latter half of my talk. Okay. I'm mostly going to hide it for right now. Okay. But one thing I maybe sort of want to comment on is if you sort of look at this formula C1, okay, let's think about what happens in this special case r equals 2. Okay. If you're asking for a repeat, okay, then this term here is going to be -1. That can be pretty small, especially if q is pretty big. Okay. And so you should expect this term to be sort of about -q over 2. Okay. that's going to be some sort of large and negative bias against repetition. On the other hand, if you're not asking for a repeat, this will only just be 0. These will sort of simplify, and you'll just get 1/2. That's pretty small, okay? And positive. Okay? And so we sort of have is this large negative bias against repetition. Okay? And some of what I want to say sort of later on about C2 is going to relate to the size of C2. How big do we expect it to be? And indeed, we should probably expect it to be pretty sizable because we saw a lot of variation when we actually looked at the data mod 5. Okay? But all right, this is a completely explicit conjecture. Okay? For it to be a value, we should better be able to make predictions from it. Okay? So let's look at a simple case, q being 3 or 4. And in this case, our conjecture takes the following shape. We think that pi xq ab is going to be a lie of x over 4, and then you're sort of going to be sort of penalized if you're asking for a repeat, or sort of correspondingly boosted if you're not asking for a repeat. Okay? And this is what our conjecture looks like. Okay. And one nice thing to observe here, okay, is that both of these terms sort of point in the same direction. Okay? Both of those terms are positive. And so what this means is that both of them are sort of acting as a penalty against repetition, or both are acting as kind of a boost in favor of switching. Okay? And from this formula, it's sort of clear that for a sufficiently large x, sort of one sort of switching patterns should beat repeat patterns. Okay? And in fact, we have a very precise conjecture for what sufficiently large should be. Okay? In fact, our conjecture is that once x is at least 5, you should always sort of have more switching primes than repeats. Okay? And the way you should interpret this 5 is as soon as you have any primes at all you want to count, okay, you have more primes that switch than repeat. Okay? All right. But again, this is something very explicit. Okay? We can see how it compares against the data. Okay? Okay. And so if we look at the primes up to 1 billion, okay, here is sort of the actual counts of patterns mod 3. Okay? I'm obviously only showing you some of the data. But this is what it looks like. And our conjecture sort of would produce the following numbers. So I think that looks pretty good. Okay. It's clearly not as good as what we saw with, say, when we were looking at things like Chebyshev's bias.
What does it mean, your conjecture? The error term just take the main term?
Yes, exactly. Okay. And I'm also sort of lying slightly by how I compute these numbers. Sort of really we have some expression that sort of says the density at height x should be sort of such and such. And so we're really integrating that expression rather than just blindly plugging into our formula. But yeah, that's basically what I'm doing. I'm sort of saying, ignore the error term. What does sort of our main term and secondary term produce?
So you're saving a log x to the 7/4.
Yeah, so when you sort of, when you distribute out like x over log to the 11/4. Okay. And so it kind of makes sense then that we don't have the right to expect sort of this data to be sort of that good. Okay. We legitimately do not think there is some sort of square root error term that like half your digits will be right. We really think there's always going to be some noise that's going to be sort of hard to sort of fight against. Okay. And well, you can extend this out farther. Okay. And I think it looks pretty good, okay, especially in view of this large error term, which you think is a legitimate error term. It's some sort of oscillatory thing, which is just going to always be there. Okay. All right. You can compare against the data mod 4. It'll look exactly the same. Okay. Things get a little bit interesting when you look mod 5. So our conjecture, sort of in this case, well, I need to tell you what this number C2 is. Okay. So again, I've sort of never written down a formula for C2. And in the case I'm not giving you a diagonal pattern mod 5, here's what it is. Okay. And in the case I'm giving you a non-diagonal pattern mod 5, here's what it is. Okay. So here chi is a complex character modulo 5. Pick your favorite one. And this number A5 chi is given by this absolutely convergent Euler product. Okay, so I do not expect sort of this particular expression to be sort of that illuminating, except what I want you to take away is that, okay, sort of this erratic term we saw is going to somehow depend on how sort of this character value correlates with these sort of L values. Okay. All right, whatever. This is something you can compute, and so you can make quantitative predictions. Okay. And again, we can do that. So here's what things look like. And if you wanted a reason to doubt our conjecture, okay, you might be able to find something on this slide. Okay. In particular, we have these two columns in the wrong order. So the top line is the actual data. The second line is our conjecture. And we think there should be more primes that are 1, 3 than 1, 2. But in fact, going up to a billion, there are more primes that are 1, 2 than 1, 3. And a billion is a pretty big number. And, well, you can go out to 10 billion or 100 billion, and you still find more primes that are 1, 2 than 1, 3, even though we think 1, 3 should win. Well, it just so happens that at about 500 billion, and seemingly sort of there ever after, 1, 3 sneaks ahead. And kind of as far out as we've computed, which has been to about 20 trillion, there are more primes that are 1, 3 than 1, 2. And indeed, so probably kind of for all x bigger than that 500 billion, you'll find more that are 1, 3 than 1, 2. So again, I take this as pretty strong evidence in favor of our conjecture. We're sort of able to get the ordering of these patterns correct, even though sort of the initial data is not obvious. And moreover, it also suggests that, again, these error terms really are big, because there has to be something else going on there for our predictions sort of at a quantitative level to be wrong, sort of initially. All right. So I want to say some words about where our conjecture actually comes from. And the basic idea is actually pretty simple. So we're going to start off just by writing down some actual expression for this function pi x q a b, which we're then going to appeal to some pretty serious conjectures to try to evaluate. And I'm going to do a lot of horrible hand-waving during this part of the talk. What we do in the paper is much more careful. I'll say some words about that. But mostly I want to give you some idea of where this comes from, in particular where sort of you see a bias arising. So in particular, if we want to count primes that are a mod q, such that the next prime is b mod q, well, we'd better start off by counting primes that are a mod q. And then we know we need to switch to a prime that's b mod q, which we're going to do by adding h, congruent to b minus a. And then we want these two things to be consecutive primes. So we want nothing in the middle to be prime. And so we're going to have some expression like this. So this is a completely true unconditional statement that is also absolutely useless if you want to actually prove anything unconditionally. Luckily, I'm not trying to. I'm not even trying to be sort of rigorous exactly about where our conjecture comes from. So let me do something completely awful. Let me replace this characteristic function by its expected value. And OK, I'm sort of lying slightly here because, OK, we're actually controlling everything at q by hand. OK, we're sort of rigging our numbers to be relatively prime to q. So it actually turns out these numbers are sort of relatively more likely to be prime than sort of a random number. So you have some sort of Archimedean or some correction coming from q. Turns out to be this. And now, this thing is actually pretty nice. You'll notice there's no dependence on t here. This is just going to be some sort of exponential function in sort of the number of terms in this product. And if you actually sort of work out what that turns out to be, it'll give you something like e to the minus h over log x. All right. And then we're going to use the analytic number theorist's favorite trick and interchange the order of summation. All right. So that means we're left to try to evaluate this sum. And now, in order to handle this, I think we have to invoke what's called the Hardy-Littlewood conjecture. This is something I imagine many of you are familiar with. But if you're not, it sort of looks like the following form. If you look at sort of counting primes in this form, you're sort of saying how often is n a prime and n plus h a prime. Well, you could do worse than by saying, well, this has to be a prime, so it's got probability 1 over log. This has probability 1 over log of being prime. So maybe x over log squared should be your baseline guess. But then you remember that, OK, if h is odd, you're not going to get any primes of this form. And so correspondingly, if h is even, you sort of have to boost up the size of your sum a little bit. And so you have this thing called the singular series that does exactly that. And this turns out to be the right expression for it. All right. OK, once again, we're actually sort of doing things where we are controlling the conditions modulo q by hand. So I need to sort of modify this very slightly to do that. And it just sort of takes the following shape. All right. So this is the Hardy-Littlewood conjecture. And so we can just go ahead and take this, plug it in here, and use that to evaluate this sum. And what that gives us is this. All right. So now we have to understand what to do with this sum of singular series with this very smooth weight. Well, as a result of Gallagher from the 1970s that singular series tend to be 1 on average. Okay. So Gallagher was using this to prove that the primes sort of behave like a Poisson process with parameter log, okay, which actually, if you sort of parse through what I said earlier, actually gives you another explanation for why you might expect the sort of e to the minus h over log type behavior. At any rate, sort of you could do worse than to sort of pretend that the singular series is 1. Okay? And if you just take that and blindly plug it in, okay, let's see what we get. Okay. Well, we'll get something like this. Now this sum here, okay, is a geometric series. Okay. I could evaluate it exactly. I could also evaluate it asymptotically. And it turns out to be of size about log x over q. Okay. And just sort of canceling things out, what you get is 1 over phi squared x over log x, which is exactly the main term we are hoping to produce. Okay. So again, we're trying to count primes that are a mod q, such that the next prime is b mod q. And again, this is sort of our naive probabilistic guess. Okay. So the question is, where does this bias come from? Okay. Well, I've lied to you horribly in many places so far. Okay. But it turns out I don't have to be that much smarter to tell you where, at least sort of initially, where the bias comes from. In particular, I only have to be smarter at this step here. So let's consider this sum of singular series. Okay. So the singular series sort of in kind of for just 2 entries, so 0 and h, you can really just think of as a multiplicative function. Okay. This is something you can evaluate sort of very easily. Okay. And in particular, it turns out that if you sum over the residue class 0 mod q, okay, you get this log x over q that we said you should get by sort of pretending it's 1. Okay. And then you get this sort of negative log x term. And you get this O of 1 term, which, if you sort of care about really sort of actually pinning down a precise formula for pi x q a b, you would care about a lot. But for right now, I don't care. Okay. And what I want you to observe is that it turns out that if you sum over a residue class that's not 0 mod q, you don't get this negative log x factor. So what this actually says then is that, well, in our sum here, if a is equal to b, we're going to get this minus log x penalty. Okay. Whereas if a is not equal to b, we're not going to get that penalty. And it turns out this is really sort of the source of sort of this bias against repetition. Okay. To find out sort of all of this crazy C2 bias to create all of the erratic behavior we saw when we looked at mod 5, well, you need to be much more careful. Here, you'd also need to be much more rigorous sort of quite a few places along the way. Okay. But just sort of at first order, this is sort of where this bias against repetition comes from. Okay. And just to say, the reason for this is just that only the first Dirichlet series has a pole at s equals 0. It sort of turns out that the second one doesn't, and so you don't pick up a term of this type. OK. So I have been lying horribly. Suppose I didn't want to lie to you. Okay. How would I be able to tell you the truth? Okay. Well, we kind of need to go back to the very beginning. We need to be much more careful with our first step, where we replace the characteristic function by its expected value. And so maybe your first thought on how you might handle this is, well, we're already invoking Hardy-Littlewood. Maybe I should just expand out these terms, okay, and then just sort of invoke Hardy-Littlewood for sort of all of the tuples you sort of get as a result. Okay. This is a bad idea. Okay. This gives you a very ugly expression, okay, which turns out to be not obviously convergent. Okay. It's very hard to analyze and sort of figure out sort of the main term, let alone secondary terms, from this expression. Okay. And moreover, you want to remember that our really terrible naive guess actually got us pretty far. Okay. So somehow it's sort of better to incorporate this expectation into whatever we're doing with Hardy-Littlewood. Okay. So it turns out to be a much better idea to incorporate that along with sort of the inclusion-exclusion procedure kind of implicit here into the Hardy-Littlewood method itself. Okay. And so the ideas here go back to work of Montgomery and Sound. Sort of in some work they were doing to prove that Cramer's conjecture is wrong quantifiably in a certain sense. Okay. But what we want to do is we want to say, well, let sort of 1 tilde be sort of the characteristic function minus its expected value. Okay. And it's sort of natural to come up with a version of the Hardy-Littlewood conjecture that sort of says, well, if you get rid of this expected value, okay, what should you predict? Well, you see some sort of arithmetic factors of the type we saw earlier. You see some Archimedean factors, and you see some singular series. Okay. And it actually turns out that this singular series has a very nice interpretation. Okay. It's just what you get by doing inclusion-exclusion on sort of the sub-singular series. Okay. All right. And so then the question is, well, how do we use this? Okay. Well, in their work, Montgomery and Sound observed that actually if you sum sort of these singular series in a box, you actually get a lot of cancellation. In particular, they observed that sort of if you sum over a box of tuples of size k, you get something basically of size h to the k over 2. And in fact, they get a main term. But really what's sort of important to observe here is that there is a lot of cancellation. So with Gallagher sort of singular series where 1 on average, this is basically picking off the 1 and sort of looking at sort of smaller terms. Okay. And the point sort of at the end of the day for us is that we don't need to worry about singular series with more than 2 terms. Okay. We're able to sort of restrict ourselves to a very small set of singular series to work with, which we can then analyze directly. Okay. And just sort of to give you some flavor of how that works, the tuples you might work with might be just 0 and h. You're sort of asking for n and n plus h to be prime. That's exactly what we just did. Okay. That contributes to the main term and the bias against the diagonal. That is what we just saw. Okay. You could imagine sort of there being one thing kind of in the middle screwing up sort of your consecutive primes. Okay. Sort of think of these maybe as like an interloper. And it turns out this is what creates the bias sort of at the level of C2. And then finally, you could imagine sort of working with a singular series of 2 interlopers. And this just sort of serves to kind of, it's unbiased. It sort of serves to make the overall mean 0, because you sort of need to have happen. Okay. So I don't really sort of intend for this slide to be super helpful. Okay. But this is sort of the flavor of what happens here. Okay. And I should say, we do sort of expect that larger singular series will play a role in this story. But it actually turns out to be pretty hard to figure out exactly what those contributions should be. We have some guesses about sort of the order of magnitude, but we've yet to be able to sort of pull out a precise asymptotic from what those terms should contribute. Okay. All right. But OK, and again, this sort of brings us back to a conjecture of this type. Okay. And when you sort of assemble everything together. And so far, I've said basically nothing about this number C2. There is some recipe to compute it. It's given by some sort of hideous thing. But the question is, how does this thing actually behave? Okay. And so that's what I want to start talking about now. Okay. So let's do that. Okay. So if Q is prime, then it turns out you have a very nice expression for how the diagonal patterns should behave. And it's just given of this form. And basically what I want you to look at and see here is that this is of size Q log Q, basically. Okay. On the other hand, it turns out that the non-diagonal patterns are given by a sort of a much uglier expression, sort of the most interesting part of which is given of the following type. Okay. So I'm taking C2, I'm dividing by Q, okay. And then it turns out to be given by some sort of average of L values, twisted by some absolutely convergent product. Okay. And this little O of 1 here is some completely explicit term. It's just sort of that in what I'm going to be talking about right now, I'm going to be letting Q go to infinity. And so I kind of don't care how this thing behaves. And the kinds of questions we're interested in are, well, how big sort of is this term C2 typically? You might also ask sort of what are the A's and B's that give you the biggest C2s and things like that. We have some work along those lines, not something I'm going to talk about here, unfortunately. Okay. But you can ask, how is this thing distributed? Well, let's just think about how sort of a typical value of C2 given by sort of this average value of L values should behave. Okay. Well, L1 chi is typically size about a constant. Okay. So for example, using work of Granville and Sound, sort of building on earlier work of people like Elliott, you can say things like 99.9% of the time, L1 chi is going to be about its average value, which is not 1, but close to 1. And similarly, you can say that L0 chi, using the functional equation, is typically of size about Q to the 1/2. So in our expression, we can just go ahead, replace L0 chi by about Q to the 1/2, L1 chi by about 1. This absolutely convergent product doesn't really matter. So what you should expect is something of size maybe Q to the 1/2 times some angle. Okay. And well, there's no reason to expect these angles to correlate in any particular way. You should probably expect about square root cancellation in these angles, which might give you something of this type. And so you should expect this thing to be of size about 1 on average. In other words, we should expect that C2 divided by Q is about 1. And in particular, if you sort of divide by this q, it's maybe reasonable to ask, do these C2s sort of all play in the same playing field? Okay. And this is something that Sound and I prove. Okay. That as q goes to infinity, okay, this quantity C2 divided by q has a continuous limiting distribution. Okay. This is some non-universal distribution. It's not like, oh, it's distributed like a Gaussian or something like that. It just sort of the distribution is what it is. Okay. But what this sort of means, among other things, okay, you can sort of take limits like this and know that they exist. They're non-zero. They behave continuously as a function of tau. Okay. And what turns out to be sort of interesting here is that this distribution, if you look at its tail probabilities, what is the probability that C2 is really big? Okay. Well, it turns out that you get doubly exponential decay. Okay. If you sort of look at this distribution, the probability that this thing is greater than tau decays like e to the minus e to the tau. Okay. So it is very, very unlikely for this number C2 to be very big, but it is typically of size about q. Okay. All right. And this might look sort of familiar to you. Sort of in reference to this work of Granville and Sound and Elliott that I mentioned earlier, this looks a lot like the distribution of L1 chi. Okay. And maybe this sort of makes sense to you because C2's definition sort of involves some sort of average of L values. Okay. But I'll also give you a little bit later on some other reasons to think about this that might make sort of the connection to L1 chi a little more obvious. Okay. But all right. I don't really want to tell you so much about where this result comes from, but I wanted to give you some ways of thinking about it. Okay. So here is what C2 divided by q is given by. It's, again, this sum of L values. Okay. Well, let's look at a very slightly simplified version of this. So all I'm doing is I'm getting rid of this Euler product that is absolutely convergent. It doesn't really matter that much. Okay. This is sort of another thing that's sort of interesting to look at. Okay. And sort of surprisingly, it actually turns out this is connected to some other quantities from analytic number theory. Okay. And in particular, it turns out that this particular thing is related to Dedekind sums. Okay. So the Dedekind sum, if you're not familiar with it, first appeared in work of Dedekind on sort of the transformation properties of the eta function, in particular sort of working out the multiplier system for eta. Sort of these Dedekind sums appear naturally. They also appear in a few other places. But what they're given by is the following sum. So here I am sort of using that q is prime. I'm assuming that kind of throughout the remainder of this talk. Okay. So you sum over the residues mod q of the sawtooth function evaluated at x over q times the sawtooth function of ax over q. Okay. So in particular, let's pretend that a is 1. Okay. Okay. Then you're just sort of summing psi squared, okay, over these things. You should get something that should basically approximate the integral of psi squared, okay, which is 1/12. And on the other hand, though, if a is pretty big, okay, it's going to be kind of shuffling this other factor around a little bit. Okay, and you should expect it to be smaller. Okay. So in particular, it turns out that these Dedekind sums are large when a over q is close to a rational with small denominator. Okay. Making precise what I just said a little bit earlier about a equals 1, you can actually come up with an exact evaluation, okay, of what the Dedekind sum SQ of 1 is. Okay. But on the other hand, somebody say a question? No. OK. Heard something. Cool. All right. On the other hand, sort of typically, it's going to be a lot smaller than this. Okay. And in fact, it's actually going to be surprisingly small. Okay. So you're summing up q things. Okay. You're expecting some cancellation. Probably you'd be sort of expecting me to say, OK, you're going to get like square root of q. Okay. Actually, it turns out that typically, you get something of size log q. Okay. This Dedekind sum, this is a result of Vardy from 1993, that if you sort of normalize by log q, you get a limiting distribution. Okay. Okay. And it's distributed according to the Cauchy distribution. Okay. So what this says is that most of the time, this Dedekind sum is going to be pretty small. Okay. But the Cauchy distribution is a little bit weird. Okay. It's given by sort of the following measure. Okay. But this thing actually has infinite expectation. And that sort of makes sense because, again, well, most of the time, you're going to be pretty small. But you have these very huge values that sort of contribute. Okay? And they sort of arise when a over q is close to a rational small denominator. So you sort of have this very small set that sort of has large mass. And these sort of typical things have very small mass. And that's a kind of unsatisfying scenario. Okay? And if you want something that sort of maybe sort of evens that out, okay, it's actually pretty reasonable to instead look at the Fourier transform of this thing. Okay. So consider the sort of mod Q Fourier transform of the Dedekind sum, defined in this way. And it actually turns out, okay, that sort of the motivating thing I was talking about, sort of this sort of simplified sum of L values, is actually equal to the Fourier transform of the Dedekind sum. Okay. And so what Sound and I are able to prove, using sort of the same kind of ideas that go into our study of C2, is that this Fourier transform has a limiting distribution. It's continuous. It exhibits doubly exponential decay, things like that. All right. So that's something I like. But I said there's some sort of connection to L1 chi. Where is that coming from? Okay. Well, it turns out that if you actually grab this expression, you can rewrite it in a more useful way. So just using the Dirichlet series for L1 chi, okay, and a very nice evaluation of L0 chi in terms of the sawtooth function or in terms of Bernoulli polynomials, if you prefer, okay, you can just go ahead, plug this in, expand out, and invoke orthogonality of characters to arrive at a different expression for this thing is the following type. Okay. So here, B bar is the inverse of B mod Q. Okay. And so how you should be thinking about this is, well, you've got the sort of 1 over B that is very reminiscent of L1 chi. Okay. You have now, instead of a character chi of B, which again you sort of think is going to oscillate and cancel as you sum over a complete set of residues, here you're now using the sawtooth function, okay, evaluated at TB bar over Q. Okay. So again, if you sum over a full set of residues, this will cancel. This looks a lot like a character, except it's not multiplicative or anything like that. Okay. And indeed, sort of the study of L1 chi is kind of what motivates our study of this expression here. Okay. So the idea, or the question is, well, how do we actually do that? Okay. Well, what we're going to do is we're going to compare to a suitable random model. Okay. We're going to say, how should this thing sort of behave typically? Okay. And well, sort of kind of all of the game is in this sort of B bar. How should you think about B bar? Okay. If B is very, very small, okay, like B is 1, you understand the inverse of B. Okay. If B is 2, it turns out you also understand the inverse of B. It's just Q plus 1 over 2. Okay. But you start getting more and more possibilities as B increases. And in particular, this B bar is going to kind of shuffle around quite a bit. And it turns out that sort of a reasonable way to think about this is to think about it as 1 over B. Okay. So in particular, the random model we're going to compare against is this. Okay. So here I'm just sort of choosing x. I'm sort of lying slightly here, but uniformly at random for the real numbers. Okay. And looking at this sort of sum. Okay. And it turns out what we want to show is that these two things sort of typically behave the same. When I say that, what I really mean is that their moments behave the same. And so we use the method of moments. Okay. We show that the moments of this behave like the moments of this. We study the moments here, and that lets us understand the limiting distribution of this Fourier transform. Okay. And I should say, a very similar story holds when you're looking at C2 instead of this Fourier transform. Okay. Essentially, the only change is that you throw in some extra coefficients here that come from an absolutely convergent sort of series. Okay. It's really not sort of making things any harder. OK. It also turns out that this C2 is related to another quantity from analytic number theory that I think is of some interest. So what I want to do is talk about a conjecture of Montgomery. So Montgomery is considering sort of an extreme value problem, or sort of an omega type result in a pretty classical setting. So it's well known that the sum of phi of n for n up to x is asymptotic to 3 over pi squared x squared. Okay. And you can ask, OK, what is the right size of this error term? Okay. I think sort of the best known results now are of the form, say, x to the 1 plus epsilon. Certainly, you can sort of get some exponential of, I think, log to the 3/5 or something of that flavor. But Montgomery conjectures that actually the right answer should be x log log x. Okay. That is, that this remainder should be no bigger than x log log x, and it should be sort of infinitely often at least that size. Okay. And Sada and I were initially hoping we might be able to make some progress on this part of the conjecture. And for right now, sort of the reason why we had that hope should be probably pretty unclear, but I'll make the connection in just a second. And unfortunately, we can't. We cannot prove the sort of omega result here. But we can prove is that this remainder has a limiting distribution which exhibits doubly exponential decay. And so if you kind of blindly assume that you're allowed to apply these results in a sort of ridiculous range of uniformity, this would actually imply that this is sort of the right answer. Sort of the doubly exponential sort of corresponding to the double log you see here. So what is the connection between sort of the work I've been talking about and this problem here? Well, in this paper where Montgomery makes this conjecture, he also proves an omega result of the following type. You sort of get that R of x is omega of x square root log x. And the way he does this is he comes up with another expression for R of x in terms of the sawtooth function. His expression is something of the following type. I'm simplifying this very slightly.
When you say it has a limiting distribution, you mean on the logarithmic scale, or?
Not here, no. Here, you will sort of just have a limiting distribution in x, not on the logarithmic scale. Yeah. So you have this expression. What Montgomery does to prove his omega result is he makes a very clever choice of x. In particular, he takes x to be the product of the first several primes that are 3 mod 4. And actually, by doing this, he's sort of able to get that the sawtooth function actually surprisingly correlates with Mobius for small values of b. And so in particular, he's able to make this thing be very large. And so that's great. But actually, sort of looking at this expression, you realize this is very close to the kind of thing that Stein and I have been studying. We are sort of looking at this without the Mobius function. And so indeed, just sort of basically blindly applying our techniques, we're able to show that this R of x has this limiting distribution. All right. So again, to kind of give a one-side summary of this talk, we sort of have the following conjecture. And this number C2 is complicated, it's explicit, and it's also nicely distributed. So I have a little bit of time left over. So I don't want to sort of be very aggressive sort of with my time slot. But let me just sort of say maybe sort of verbally some things that are sort of related to this that are sort of surprising. So I didn't really talk at all about how longer patterns behave. We sort of, our conjecture applies equally well no matter if you're looking at just 2 consecutive primes or 100. But it actually turns out that for the most part, sort of the longer patterns almost decompose in terms of the smaller patterns. So for example, if you want to have primes, say, that are 1 mod 10 followed by 3, then 7, well, it sort of makes sense. You should go from 1 to 3 and 3 to 7. And you might hope that, OK, well, maybe I just sort of multiply these transition probabilities together, and I'll get sort of the right answer. But it actually turns out that that's not true. It's very nearly true that you sort of go from 1 to 3, then 3 to 7. But it turns out that if 1 and 7 were the same, you'd actually sort of see a lingering penalty from trying to cheat a repetition into the system. And so correspondingly, if you're not trying to cheat a repetition, you actually have to be sort of boosted a little bit. That is actually kind of the only sort of deficit to this sort of decomposition. So putting this another way, we're saying the primes mod q do not behave like a Markov process, but they sort of very nearly do in this sort of sense, apart from this sort of lingering repeat issue. Another thing you might ask is, in what other scenarios might you expect to find such a bias? And I think the right answer here is anytime you're looking at a sifted set, you should expect to see a bias. So for example, you could look at, say, sums of 2 squares. You will see a similar bias. You could look at twin primes. You will see a similar bias. You could look at square-free integers. You'll see a similar bias. But you sort of need to tweak what your notion of bias means, because it actually turns out that because sort of square-free integers occupy a positive proportion of all integers, it actually turns out that these secondary terms are actually shoved to the level of main terms. So kind of a toy problem to think about might be, what is the probability that 2 consecutive square-free numbers are both odd? And the answer is not 4/9. And so I think that's where I guess I'll end. All right. Thank you. Yep. Where does that come from? So if you imagine sort of decomposing the Dirichlet series for the singular series, okay? This thing is a multiplicative function, okay? And we care about its values on arithmetic progressions. Okay? And so very naturally, sort of the way we do this is we write it as a sum of the singular series twisted by characters chi. Okay? And then if you just go through and figure out, sort of do the standard polar analysis of this function, well, you just sort of see an L0 chi popping out as a residue. And when you do this. I should say, though, there are actually some sort of surprising properties of the Dirichlet series for this singular series with two terms in it. I particularly sort of like to think that, well, OK, if it's a multiplicative function, you just sort of play standard games with Euler products. You kind of start factoring. You pull out zeta. You pull out L0 chi. You pull out whatever. Okay? And you sort of be able to prove almost anything you want, especially since we're equipped with a very smooth weight. Okay, we're essentially weighting these L functions by the gamma function and the melon side. Okay? But it actually turns out that this Dirichlet series for singular series actually has a natural boundary at real part of s equals -1. Okay? You're not going to be able to go past that. That actually sort of creates sort of a lot of sort of the term sort of creates a barrier to sort of how good our formulas can be.
Are there any function field analogs of these things that might be provable to say the large field?
Yeah, I think that's a very good question. I expect probably so. But to be honest, I haven't really run any data on this. I haven't thought about the problem very much at all. But I think that is a very natural question. Exactly. Yeah. But I think sort of if you have the right notion for what it means for two, say, irreducible polynomials to be consecutive, then yeah, absolutely. Okay. Yeah, I think that is. Yeah, I think if you order by lexicographic order, you should certainly see a similar sort of phenomenon. Okay? And I think it'd be very interesting to try to prove that.
So with your comment about the natural boundary.
Yeah.
So if I'm understanding correctly, does that mean that you can replace your big O log x to the -7/4
Mm-hmm.
by some completely horrible but totally explicit looking contour integral that depends on x, and then you'd expect an error term of maybe, square root of x on the outside?
OK, that's an interesting question. So I think my answer is ultimately going to be no for a couple of reasons. So the first is this log to the 7/4 is actually not coming from the natural boundary. Okay? It turns out it's actually sort of coming from the fact that sort of when you write down, probably not going to get the normalization right, so let me not embarrass myself at the board. But when you sort of write down sort of the decomposition of the Dirichlet series for the singular series, sort of in this sort of Euler product kind of game, you end up with some LS chi's in a denominator. Okay? And so what this sum is really doing is it's sort of seeing, it's a sum over the zeros of sort of these Dirichlet L functions with some sort of crazy residues. Okay? And so that's sort of what that is. And so sort of under some plausible-ish conjectures, it should be of this size. Okay? So for example, we'd want to assume something like simplicity of zeros of Dirichlet L functions to actually have it be of this size. That seems sort of reasonable to conjecture. Okay? The natural boundary would contribute something sort of at the level of, I guess the way I've set this up, log to the -2. Okay? And so yeah, you're probably right that sort of that expression certainly could be sort of written down in some way. But it also turns out that, well, we still have to understand how all of these sort of larger singular series contribute. Okay? We think three-term singular series should contribute a term of relative order log squared over log squared. Okay? We think, sort of all sort of singular series should matter in some ways, sort of for lower order terms. So no, I don't know how to write down some expression that'll have a square root error term, apart from just sort of writing down maybe just the sum of singular series itself.